of which definition you're using. And so, for example, if you're using Arrhenius, then it has to be water. Because Arrhenius acids are H plus AQ, or hydronium AQ, and hydroxide AQ. But if you're looking at Bronsted, Bronsted need not be in water. The most common example of a Bronsted acid-base reaction that's not in water is this one, where we have ammonia gas reacting with hydrogen chloride gas. And what this produces is it produces smoke. This is smoke, which is tiny crystals of ammonium chloride that form, and that's solid. And so you get the suspension in air of tiny crystals of ammonium chloride. So this is a smoke generator. But you don't want to breathe ammonium chloride, probably. And so here, the base is still a proton acceptor, the acid is still a proton donor, but we don't need water. And so this is why Bronsted came along, to redefine an acid and a base. And then for Lewis, it's the same thing. We could have solid-solid reactions, or we could have alternate solvents. Alternate solvents in organic chemistry, oftentimes they use alternate solvents to decrease the strength of a particular base or a particular acid. Now, in organic chemistry, they call the bases, they call them nucleophiles, and the acids they call electrophiles. And then what they do is they change the solvent for the nucleophile, and that could decrease its reactivity, you know. And so the solvents do play an important role, and solvents can definitely impact how reactive the species are, and it's another way that they can manipulate the reactions. And so that's an important point there. And the other question was here. Let's talk about, what do I want to talk about? I want to talk about like pH determination, something like that. And so we're going to go back. Let's go back to our amide example here. If I have sodium amide here, sodium amide is a soluble salt, and soluble salts are strong electrolytes. So this is not Ka. Some people think this is Kb. This is not Kb. This is just K. K for soluble salt. And so some people will say, oh, sodium amide is a strong base. Strong base should ionize 100. No, it's not. Sodium amide is a soluble salt. Soluble salts ionize 100% because they have a very large K. I don't know the number here. So if I start off with 0.1 molar here, initial, and then there's going to be change, equilibrium, and 0 here, 0 here, we're going to lose all of it. And it's going to go to 0.1 molar sodium and 0.1 molar amide. And so this isn't what makes sodium amide a strong base. What makes sodium amide a strong base is amide itself. Amide is a strong base, and what do strong bases do? Strong bases hydrolyze water. And they're going to hydrolyze water to form, in this case, ammonia and hydroxide here. And so we saw, this was from the quiz thing. This was 1 times 10 to the minus, or 42, 1 times 10 to the positive 42, which is huge. It's huge. And so if we start off with 0.1 molar here, then, you know, essentially, practically all of it's going to react, and we end up with a very small quantity over here, but we end up with like 0.09999999, etc., molar hydroxide. So when I'm doing these problems, you have to see what they're asking for. If the problem's asking for pH versus inventory, if the problem's asking for inventory, I do all the steps. However, if the problem is asking for pH, I might take a shortcut here because it's a base. So base solutions, we look for hydroxide producers. And so amide's a hydroxide producer, but there's also one other hydroxide producer present. And what is the other hydroxide producer present? Water. And then I ask myself, do I expect Kw to contribute much additional hydroxide? Well, the maximum amount of hydroxide I'm going to get from Kw is 10 to the minus 7, but due to the common ion effect, that is, we already have a whole bunch of hydroxide present to begin with, am I going to see that much? And so bases produce hydroxide. This is, for us, we're doing aqueous solutions. So Ka, Kb is only with water as the solvent.
What's the number on Kb if 1 times 10 to the y?
Positive 42. Let me redo that. And so when I look at Kw, it's going to produce hydronium, both hydronium and hydroxide. But this is called the common ion effect. I'm starting here with a lot of hydroxide from the previous step, because hydroxide is common in both steps 2 and 3 in this particular instance. So that's 0.99999. And then I'm starting with 0 hydronium because I'm going to imagine nothing's happened yet. Water is pure liquid, so we can ignore that. And so this is going to be plus X molar and plus X molar. So my question is X going to be significant or insignificant? And the answer is the biggest X can be is 10 to the minus 7 when both of these are 0. The initials are 0. So if I have no common ion, I'm going to get the maximum amount of hydroxide. So if there's no common ion, that is it's 0 and 0, then I get the max X because I need to make sure equals Kw. Kw is 1.0 times 10 to the negative 14 at 25 degrees C. So here, if I want the to know how much additional, I'm going to at the most expect 10 to the minus 7. 10 to the minus 7, more like 10 to the minus 8, 10 to the minus 9, 10 to the minus 10. If I add 10 to the minus 10, that's 9 zeros. If I add something that has 9 zeros, is that going to impact this number? Significant? No. And so if I'm only interested in pH, this is probably what I'd do. I'd stop here, but pH is the power of the hydrogen ion concentration. I don't have the hydrogen ion concentration. Don't I need to? If I did step 3, then calculating pH is easy. So calculating the pH from step 3 here is the pH is equal to the negative log of the hydronium concentration. And the hydronium concentration we get from the final step here. That's one way. However, if I wanted to take a shortcut, then I'm going to take advantage of the relationship between POH and pH. That is, from here I can say that the POH is equal to the negative log of the hydroxide concentration at equilibrium. Well, the equilibrium hydroxide is, I'm going to say step 3 is negligible in this particular case. So if step 3 is negligible, then I'm going to say that step 2 is where I'm going to get all the hydroxide from. Okay, then once I have the POH, then I'm going to use the relationship here that the pH is equal to the pKw minus the POH. In other words, the pH plus the POH equals pKw. And so I'd stop here. And the definition of a base solution is that the hydroxide concentration is greater than the hydronium concentration. And they have a seesaw type relationship. So if the hydroxide goes up, the hydronium has to go down because it has to equal this constant, the product. This is called the ion product. The ion product has to equal this constant. So one side goes up, the other goes down. So no matter what solution, acid, base, or pure water, both are going to have hydronium and hydroxide. Okay, so again, the point of this is that if I'm interested in pH, sometimes I'll take a shortcut. If I'm interested in inventory, I'll do the whole thing. And so that's something we consider in all problems. So I'm going to move on to, and then the other thing is we have to worry about what? We have to worry about simultaneous equilibria. Right? When do we worry about simultaneous equilibria? So what we're going to do is the stepwise approach is by far the easiest. So what we're going to try to do is do everything stepwise, but that's not correct, you know. It's not totally correct because what happens is this. I'm going to add X here, but X is going to be kind of negligible, but it's going to change the equilibrium concentration here of hydroxide. Now, all these steps are in the same beaker. And so I can't have two different hydroxide concentrations in the same beaker, can I? No, it has to be the same hydroxide concentration for all of these. So what happens is this perturbs this step. But this step is going to perturb it negligibly. We're going to add so little that we don't worry about the change here, and it's still going to be in equilibrium. And although it's not 100% correct, it's close enough here that we won't worry about it. All right, so now we're going to go to polyprotic acids and polyprotic bases, or not polyprotic. Polyprotic only stands for acids because acids contain protons. And so polyprotic acids. And what should I say about bases? What I should say is maybe polyhydroxic bases. But do all bases contain hydroxide? Did amide contain hydroxide? No. And so rather than calling it all acids contain H plus because this is all Bronsted. We're not dealing with Lewis here. So all acids contain H plus, but the bases don't. The bases hydrolyze water to produce hydroxide. And so what we're going to call the bases, we're going to call them polybasic bases rather than polyhydroxic bases. So probably the most common polyprotic acid is phosphoric acid. So our example is going to be 3.0 molar H3PO4. Phosphoric acid is a triprotic acid, but all three hydrogens don't break off at the same time. So there's a collision with water here, and that collision with water is just going to knock off one of the hydrogens to produce hydronium and dihydrogen phosphate. We have to remove the first hydrogen from all the phosphoric acids before we start removing the second hydrogen. That's because the second hydrogen is much weaker acid than the first hydrogen. It's easiest to take the first one off. It's much harder to take the second one off. And so we're going to have to complete this step before moving on to the next step. So,
Was that say 3 molar?
yes. 3 molar is kind of high, isn't it? 3 molar, well, in lab, 3 molar is not high. In lab, we'd call 3 molar dilute. 6 molar phosphoric is no big deal. But for our calculations, it seems kind of odd, doesn't it? Because why isn't it like 0.3 molar? But in lab, 0.3 molar is like water. It's not going to do anything. I'd rather use the 3 molar, 6 molar, 12. Give me the 12 molar stuff, even though I got to be a little more careful. But I want the reactive stuff. I don't want the weak, watered down stuff. It's like lemonade. You're drinking just water, overly diluted lemonade. I want like the concentrated stuff. Yeah. So that's a good eye. You caught that. You know why? I'm using the book's example. In the book, they don't want to do the quadratic equation. And so one way to avoid the quadratic equation is make the initial big. If you make the initial big, then chances are that the change is going to be small relative to a big initial. The bigger the initial, I mean, I could use 30 molar here, but it's impossible to get 30 molar phosphoric because that's a higher molarity than pure. Like pure water is 55 molar. You can't get higher than that. But anyway, so we're going to make this big, but not too big, because if we make it too big, then what kind of error are we introducing? Activities, yeah. If we make it too big, then we shouldn't be using stoichiometric concentrations. We should be using effective concentrations. In fact, at 3 molar, we probably should be using effective concentrations, because if you go back to the table in chapter 14, the table in chapter 14 maxed out at 1 molal. 1 molal is not that. Already at 1 molal, you're seeing significant, 1 molal is about 1 molarity. So 1 molal, you're seeing significant different deviations, and now we're at 3. I'm starting to worry that this calculation's not going to be very good. I'm starting to worry I'm going to have low confidence in this calculation, basically. Yeah, low confidence in the calculation, that's okay. You know, we can say, oh, I don't have that much confidence in this calculation. I saw an interesting, I was watching this YouTube, it was yesterday, and they were talking about something. It was a test, and the students had to write the answer, and they had to say something about their confidence in the answer. How confident were they that the answer was accurate? Antonio's shaking his head no, yeah. And I thought, wow, man, maybe I should do that. Huh? Just to see. Because there's a super famous, this isn't the first time I saw something like that. There's a very famous quote from a very famous physicist who said, it's not, the important thing is not getting the answer. The important thing is getting the answer and knowing how much confidence you have in your answer. You know. So anyway, here I would say I'm not going to have that much confidence because I'm going to go ahead and use the stoichiometric and not the activity here. But it's okay because I don't know how far off I'm going to be.
What is it about the bonds that phosphate has with the hydrogen that it makes it so that one of them is easy to lose, but the other two it's not as easy?
Okay, that's an important thing for the end of chapter 17. The end of chapter 17 we talked about in Chem 1A. We covered the structure and acid-base properties. Did you guys cover that in Chem 1A? Structure and acid-base? Who did you have, Ashley, for Chem 1A? All right. So you don't remember if you covered it or not. Actually, you might have covered it, but just might not have remembered it. That's an interesting thing because I was looking at the quiz and I realized, oh, I have a question just like yours on the quiz. But I haven't gotten there, and then I wondered how many people covered it in Chem 1A and not covered it. Probably a lot of people didn't cover it in Chem 1A. So let me save this because Word crashed this morning. And I forgot to add pages. Let me give you the simple answer. It's going to get successively harder to remove the H plus because the negative charge goes up. The higher the negative charge, the stronger the electrical attraction is, making it more difficult. And so if we have a 2 minus ion, and it's going to go to 3 minus. So for example, if we tried to pluck off the hydrogen, it's a tug of war. And all of these are tug of war because who are the participants in the tug of war? The participants are water. Water is trying to pluck it off. And so we have an H plus that's in the middle of water versus phosphate. Phosphate I'm going to draw as an octet here. I'm going to follow the octet rule. And so here, water is going to have an easier time fighting against, let's say, a dihydrogen phosphate than a phosphate. And so here it's going to be hard to pull off because phosphate doesn't necessarily want to let go. The hydrogen is attached not to the phosphorus. In acids, the hydrogen is always attached to the most electronegative element in their Lewis structure. So some people put, like in Chem 1A, some people put the hydrogen on phosphorus. The hydrogen does not go on phosphorus. The hydrogen goes on oxygen. Probably should draw this a little differently. So we think about the tug of war here. Water is going to have a harder time pulling the H plus from phosphate than it's going to have versus dihydrogen phosphate. Just based on the charge. And that's essentially what we're looking at here. Because this whole thing is a 3 minus. And I'm doing dihydrogen. I could do monohydrogen too. But this is just minus. So we'll look at acid-base strength later in more detail.
So at room temperature, we will have a non-zero number of just phosphate in there, or yeah, just phosphate with no hydrogen,
Yeah.
and that'll be determined by the Ka of the initial.
Mm-hmm. Right. If we do this stoichiometrically, we expect 3 times 3, which would be 9 molar H plus and 3 molar phosphate. You know, if this were a strong acid, we'd say we have 3 molar H plus and, or 3 times 3, which would be 9 molar H plus 3 molar phosphate. But that's not what we get because only one hydrogen breaks off at a time and it gets successively more difficult. So the amount of phosphate we get at the end is actually quite small. We'll look at it because we're going to do the whole calculation. We have to look at Ka. Phosphoric acid is borderline strong. And so can you see what the Ka for phosphoric acid is? Yeah, times 10 to the negative 3. Why do I say borderline strong? Because right at the border is, what is it, bisulfate? Or oxalate ion. Or no, oxalic acid. Oxalic acid is right at the border, and it's 10 to the minus 2. Do you see that? So 10 to the minus 2 is right at the border for the weak acids, and phosphoric acid is up there. It's close to 10 to the minus 2. So it's still a weak acid, but it's one of the stronger weak acids. All right, now what we're going to do is we're going to go ahead and calculate what happens here. So that it's going to be a change. Change is going to be minus X molar, plus X molar, plus X molar. And so at equilibrium, I'm going to get 3.0 minus X molar, and X molar, and X molar. I'm using the book's example here. The book picked 3 molar. Do you know why the book picked 3 molar? I'll show you why the book picked 3 molar. And so we're going to get here the hydronium times the dihydrogen phosphate concentration divided by the phosphoric acid concentration. So this is just going to be x squared divided by 3.0 minus x. All right, what I'm going to do is, the k is 10 to the minus 3, so it's kind of small. I'm going to assume that the change is small and use the simplifying assumption. So we're going to use SA here. If we use that, we're going to just say x is much smaller than 3, so that 3 minus x is just 3. And so I'll just put 3.0 here. So that means x is equal to 3 times 7.5 times 10 to the minus 3, which is what, 0.0025 or something? Let me check that. I'm just going to do it in decimal form. 0.0075 times 3. 0.0225. Okay, what do we do next? Yeah, can you calculate the percent change and tell me what it comes out to? Oh, did I forget to square root it? Oh, yeah. Can you, sorry, can you redo my calculation for me? We'll need to take the square root of this. 0.15? Okay, then can you calculate the percent change? Five? Right on 5? Yeah. So the percent change is like 5.000%. Right on. So now, do you see why they picked 3 molar? They picked 3 molar so that we could use the simplifying assumption. That's why. And any lower than 3, the simplifying assumption would fail. Any higher, then we're pushing it because of the activities, right? And so they just chose 3, which landed right on 5. But, you know, 5%, okay, it's acceptable, but how much confidence are you going to have in that x value? Maybe not the highest confidence, because we're right at, I mean, like 5 is okay, but 5.01 is not? 5 is okay, but what about 5.4? You know, surely 5.49 rounds down to 5, right? And so we aren't going to have as much confidence. Well, how does that translate? Let's see what happens here. So this is pretty simple. This is just going to be 3.0 minus 0.15, which is going to give me 2.85 molar. And then I'm going to get 0.15 molar here, and then 0.15 molar here. And then one thing I can do after this, after I get the equilibrium concentrations, what should I do next? Yeah, I'm going to plug them back in to check my K value. And so this is going to be 0.15 squared divided by 2.85. And what does my K value come out to? .007894, which is 7.894 times 10 to the minus 3. And then I compare it, the two K values. So I have this K value here, and I compare it with the accepted K value here. Is it good enough? So our calculated K value came out to about 7.9. Our accepted K value is 7.5. Then I double check well, it's off, isn't it? Is it off due to rounding? No, we didn't round anything. So it's not due to round off error. It must be due to calculation. We redo the calculation comes out the same. Why is it off? Because the simplifying assumption is throwing it off. We can't have as much confidence in it because we're at the limit of what's acceptable. You know what would be better here? You know, if I got 5% change, it depends on how much time I have. If I'm like pressed for time, I'll accept it. You know, 5% change, I don't have enough time. If I have enough time, then I'd want a better answer. How would I get a better answer than this? Quadratic. And so what we're going to do is this is kind of at the limit of what's acceptable. So instead, I'm just going to get this into quadratic form. So alternately, I don't like how big the error is. 7.9 times 10 to the minus 3 is kind of a big error. But big is relative. You know, if it's multiple choice, you're probably close enough. Kind of a big error because our simplifying assumption was at the limit. And so instead, what I'm going to do is alternately, we'll try the quadratic. And there we aren't making any kind of assumptions. We should get an accurate answer. And so if I do the quadratic, I'm going to get x squared. I'll just get it into quadratic form. X squared. I'm going to write it in decimal form. 0.0075 x minus 3 times that, which is 0.0225. Minus 0.0225, and this is going to equal 0 here. Okay, and then I'll get my quadratic solver here and just plug in the numbers here. And so B was .0075, and C was negative 0.0225. At least I think. I need to scroll this over a little bit. Yeah. And then let's calculate it. So you might think, well, with the simplifying assumption, we got an x value of 0.15. However, if we use the quadratic formula, we get an x value that is 0.146297. You might go, well, 0.146 is just going to round to 0.15, isn't it? But if we round that to 0.15, what we're doing is we're introducing a lot of round-off error, and we're going to get the same k value. And so instead of rounding it, I'm going to just carry the extra digits here and then calculate k again. And so this is my second attempt at calculating k, but this time I'm going to use the value that we get from the quadratic, 0.146297 squared, divided by 3 minus this. 3 minus that is going to be 2.85. I don't want to do this in my head. No. This is going to take too much of my brain power. I'm just going to do it here. 3 minus, I have very limited brain power. 3 minus 0.146297. I'm likely to make a mistake. 2.853703. Okay, let's invert that times 0.146297 squared. All right, now I get 0.00 0.075000139. So this looks good. Match for 7.5 times 10 to the minus 3. So the quadratic gave us a better answer. Okay. Now, if I'm only interested in the pH, I could potentially stop here if I think step 2 will be negligible. Now, how do I know if step 2 is going to be negligible? So let's go ahead and take a look here. Step 2. And so what I'd do is, which concentrations I'm going to carry down? So we make a compromise, you know. Sometimes we could live with an answer that's not as good, like this, 7.89. If it saves us a lot of time. And so what I'm going to do is I'm just going to use the simplifying assumption answer here, even though it's not as accurate, because I don't want to write all these digits. Writing all these digits is going to take too much time. And so that's a sacrifice that I'm willing to make for this particular problem. And so let's take a look at step 2. Once we've deprotonated the first hydrogen, then we can start deprotonating the second hydrogen. And so we'll take dihydrogen phosphate, H2PO4 minus, and now the water can attack that to form hydronium and monohydrogen phosphate, HPO4 2 minus. Now what I'm going to do is I'm going to look at the Ka value for dihydrogen phosphate. The Ka value for dihydrogen phosphate is equal to what we call Ka2 for phosphoric acid. Ka2 means taking off the second hydrogen of phosphoric acid. And we could look that up on the chart up there. If you look for dihydrogen phosphate, I see it up there. It's 6.23 times 10 to the minus 8, correct? 6.23 times 10 to the minus 8. Now, you have to recognize this chart has old data. Our book has newer data. So these numbers might not match the same ones in our book. But I don't want to look at the ones in our book. We'll just recognize that different charts, depending on the date that they were published, are different. Although that one's deceptive because this one was published 1998. But this data is from maybe from the 1950s, 1960s. It's old. They never changed it. They never updated it. So you have to be careful with that. And so, you know, there's reliable sources for data. Do you know what a good reliable source for data is? You know, you might think Wikipedia is a pretty good source, but is that updated continuously? Well, it depends on who's monitoring it. It really depends on the person or the people who are following it, right? It could be something like this where you have old data. But if you want up-to-date data, can you give me a source for up-to-date data? That you know that they look, every year they look for the latest numbers and they include the latest numbers in there, as long as they're reliable numbers, that is, they've been reproduced.
SDS. Like the SDS sheets.
The SDS is probably pretty good. SDS safety data sheets are probably pretty good for data. I mean, those have to be updated. But there's another source. The SDS data, you don't necessarily find Ka values in there. SDS mostly is contact hazards, reactivity hazards, that kind of stuff, but it's not really calculation oriented like that. There's probably two sources that are two sources that are updated annually. Do you know what those are? Ashley, do you remember what your Chem 1A instructor might have said about those two sources back then?
Oh, I didn't know that name.
Yeah, Kat?
I don't remember exactly, is it either like SIC or CRC?
CRC, right, the CRC, good. Kat remembers. That's the CRC. Does anybody remember what the CRC stands for? CRC, the acronym CRC? Or no, maybe you haven't heard it. CRC stands for the Chemical Rubber Company. And why is the Chemical Rubber Company in the business of data? I don't know why they're in the business of data, but the Chemical Rubber Company is in the business of data, and they update it every year, and you can buy a book. It's called the CRC Handbook of Chemistry and Physics, and it's published annually. I have like the 1980 edition, 1982 edition, I think it is. It's about... If you buy an old edition, it's not that expensive. If you want the latest edition, it's kind of expensive. There's a CRC, there's an online version of the CRC, and also there's another book. Does anybody remember the other book in addition to the CRC? Yeah, an AM, you got it. It's a drug company. The other book that's updated annually is the Merck Index from Merck, the drug company. But anyway, those two are good sources. So if you need reliable data, you look for data like but you have to pay for that. And I don't want to pay for it, so I'll just use this old data here. And we know our calculation is not going to be so reliable because it's already at 3 molar, right? And so it's okay. What's a little bit more? Maybe it didn't change, But actually, I know it did change because I know our book's values, but it's all right. I'm just going to go ahead and use it. And so those are things we think about. And so, Antonia, you're good. If we don't want to have to worry about the confidence in our calculation, then we wouldn't be thinking about all these things. If we're worrying about the confidence in our calculation, then we better be thinking about all these things, But anyway, let's continue here. H2PO4 minus. This is what we call a common ion. A common ion is coming from the previous step. We have 0.15 molar. And so I'm not going to use the better value here because I need to save time. This is a test or something, and I don't want to waste any time. But we have 2 common ions. So H2PO4 minus is 1 common ion. What's the other common ion? H3O plus. That's 0.15 molar, and so we're going to bring that one down too. And so what we do is we take the common ion from here, and we're going to drop it down. H3PO4 is not common, and so it ends there. And so H3PO4 stops here. Now, simultaneous says all the common ions have to have the same concentration equilibrium, but we don't want to do simultaneous because simultaneous, actually, you want me to show you some simultaneous equilibria? I'll post this. There are different methods for doing simultaneous equilibria. And so the book has the setup I did. I did the setup, and you can solve it, the setup, using some tricks. Tricks like this simplifying assumption, and tricks like rather than solving for y or x, you solve for x plus y. Those are tricks, mathematical tricks you can do. And then you can solve the equations that I gave. But there's an alternate method. The alternate method is mass and charge balance. So I'm going to solve problem number 89 in the homework using mass and charge balance. So we come up with our 2 ice tables. I didn't complete the second ice table. In fact, I didn't even complete the first ice table. If you want, if you want full credit, you complete the ice tables for both of these. And then you recognize that, okay, step 2 here will perturb step 1, depending on what the initial concentration, C is for the initial concentration. I'm using different notation here. This is the notation, I think, in the book, so that's why I used it. Usually I write just HCN I, and then over here I write HCN E. I standing for initial, E standing for equilibrium. But to be consistent with the homework, I changed the notation here. But what happens is, if you try this stepwise, then the bulk of the hydronium comes from water. HCN doesn't produce much hydronium. It's a weak acid and you have a very low concentration. C has to be very small. If C is big, then we can ignore water. But if C is small, then water becomes more and more significant. And so this turns out to be simultaneous. So to get full credit, you just have to recognize that step 2 perturbs step 1, and to recognize it, we need a value of C. And the value of C, I think they used in this particular problem was 1 times 10 to the minus 5. So if we use the 1 times 10 to the minus 5 molar here, then we see that most of the hydronium comes from step 2. Something like that. So what that means is we have to do this simultaneously. So last time I came up with, remember we came up with y plus x, and we got y plus x here, and then down here we had x plus y. Do you remember that? This is going to be different. This is going to be solving simultaneously using mass and charge balance. So we have our equilibrium constant expressions for step 1 here and step 2, right there. But what we want to do is we want to generate more equations for this. And so I'm going to call that equation 1, or equation A. I call it equation A, equation B. And so if we have 2 unknowns, we just need 2 equations, but sometimes the math is kind of horrendous just for those 2. So we want to generate as many equations as possible and pick the simplest ones to solve. It's not like we're going to solve all the equations. We just want the simplest ones to solve. And so what are some of the other equations we can generate? And so let me tell you, here's the wrong mouse. Let me tell you some of the other equations I can generate. And this is it, the initial concentration of HCN. Okay, so where did all the HCN end up? All the HCN ended up in the equilibrium HCN, that is the HCN left over. But what happened to the HCN that reacted? Well, the HCN that reacted produces hydronium and cyanide. But the problem with hydronium is we get hydronium from 2 sources. We get hydronium from water and we get hydronium from HCN. And so I can't use that as a reliable indicator of how much HCN ionized or hydrolyzed. In this case, I can use cyanide, though. All the cyanide that I have came from the initial HCN concentration. So this is what this is saying. The initial HCN concentration, all that HCN that I had there initially ends up in the HCN that's left over, that is the equilibrium HCN, plus the HCN that was converted into cyanide. And the hydronium is not reliable. The concentration of cyanide, it should equal the concentration of hydronium because it's 1-to-1, but we get additional hydronium from the water. So this is why this doesn't look balanced, but it is balanced. Do you see that? And so this is mass balance equation here, 1. Okay, so C is mass balance. Now D is charge balance. That is, the total positive charge has to equal the total negative charge, right? The total positive charge, there's only 1 cation in this. What's the 1 cation in here? Is hydronium. So this is the total positive charge, but there are 2 anions present. The 2 anions present are hydroxide and cyanide. And so the total positive charge has to equal the total negative charge, cyanide and hydroxide. We just combine them. And that's charge balance. So I added a mass balance here and a charge balance. Okay, once I do that, then I'm going to solve some equations here. And so what we can do is, this is like an algebra trick. We can solve for the cyanide concentration by manipulating these here. And then we get something called the cyanide mole fraction. The cyanide mole fraction is the concentration of cyanide over the total concentration here. The total concentration would have been the equilibrium HCN and the equilibrium cyanide, or C. We could have used C here as well. And so this is the this is going to be the cyanide concentration. We take the mole fraction of cyanide times the concentration, total molarity. And so, you know, it's going to be the fraction, the cyanide is going to be a fraction of the total molarity here. This is another algebraic trick. And then the hydronium concentration we can rewrite like this. The whole reason we're doing this is to make the math easier. Otherwise, the math is going to be very difficult. but you're already thinking the math looks horrendously convoluted as it is, you know, and so it doesn't look so easy. So we do the same thing here. We did the hydronium, which is going to be substituting this is going to be the cyanide concentration at equilibrium, which is equal to the hydronium concentration. This is equal to the hydronium concentration from the HCN, plus the hydroxide concentration is going to be the hydronium concentration from the water. Okay, so I'm skipping some steps here. Okay, now once we do that, then we can simplify this here and generate this equation here. And then we do some additional tricks. Some additional tricks is sometimes we don't solve for a single variable like x or y. Sometimes we solve for a sum of variables, x plus y, like in the example in the book. Sometimes we solve for a ratio of variables, like cyanide to HCN ratio. So we solve for the cyanide to HCN ratio, we get another equation. And with that equation, we can do substitution too. So these are a whole bunch of different tricks in solving system of equations that you use.
Wouldn't the cyanide to HCN ratio be the same? Wouldn't that be equal to 1?
Would this cyanide to HCN ratio be the same? Same like 1?
Yeah.
No. No. Because HCN is a weak acid, so we produce very little cyanide. Weak acids, hydrolyze water to a small extent. So most of the HCN is going to stay unionized or unhydrolyzed, unreacted. And so it's not a 1-to-1. It's going to be a very small number.
So the thing with the concentration is equal to HCN plus cyanide, is that like the remaining HCN? Was the cyanide produced?
This one, this is the initial concentration of HCN, which is going to equal the HCN that remains plus the cyanide that's formed.
Wait, so like, actually, can we go back up for a second? I don't know if you're like actually saying this, but pretty much like, let's pretend that reaction just produced a very small amount of like the H3O and CN. So let's just say it's like, produces.
It's not a small amount. The whole reason we're doing this is because it's a significant amount.
Well, okay, let's assume it's a significant amount, that's fine.
In fact, it's going to be the biggest contributor.
Okay, so it is the biggest contributor, like whatever the CN is, let's say it produces that amount. 2 moles of that, wouldn't that also make 2 moles of the hydroxide in that equation? And so we could just eliminate that variable, we know that.
So what you're saying is, wouldn't 2 moles of what produce 2 moles of hydroxide?
Yeah. Or like for the one of them, I'm sorry, like the HCN, that reaction, right? You see how it produces H3O and the CN? It's the same amount of both, correct?
The same amount of H3O and CN?
Yeah,
No.
it's not. Like from that specific reaction.
It is, yes, because it's plus X plus X.
Okay,
But the problem is this is not really 0.
that's right.
This is, there's some hydronium in there to begin with from the water.
It's not gonna be at equilibrium.
Yeah, and so really I shouldn't have written 0 there, but I did. I did because, I don't know why I did. I did it because I think that was the book was doing it.
Okay.
But anyway, we go through all this stuff here. And then, even though this doesn't look like it's simplifying anything, it simplifies it enough that we can solve it. Because it turns out to be a 3rd order polynomial. And so doing all this stuff, we convert this into the 3rd order polynomial. X cubed plus ax cubed plus bx squared plus cx, etc. And then once we do that, then we can plug in the concentration. So that's what I did here. So I have the equation as a cube, 3rd order. Plug in the numbers here. Okay, so once we get the numbers, then this becomes easier to solve. This becomes very easy to solve. This is cubic. Very easy to solve if you have a cubic solver on your calculator. Now, for exam 16, you know, I gave you a fourth order polynomial. Fourth order polynomial, you can't solve using a standard calculator. Of course, you could solve that using a programmable calculator, you know, because a programmable calculator is a solver that can go to higher orders. So if you solved it using the solver for higher order, then I would have deducted some points from your test. But if you solved it, maybe you didn't, maybe you just didn't show your work. If you solved it without using the equation solver, like a higher order equation solver, then I'll give you credit for that. So just show it to me if I deducted. I might have deducted, I might have said programmable calculator or something because I didn't see how you solved it. I need to see how you solved it. But with a third order, then I just plug it into the calculator here. But you're thinking, why? It's so simple, just buy a more expensive calculator. Yeah, that's fine, but in science, it gets more and more, the calculations get more and more complex, so we have to do these things like method of successive approximations, you know, because the calculations just become too horrendous. And so it's not that, you know, okay, just buy a more powerful computer. And that's what people are trying. The scientists are just trying to get more and more powerful computers. So they're saying, oh, will quantum computers allow us to be able to solve these equations that we couldn't solve before? And so people are saying yes, you know. They are, but it's just an arms race. So you're just going to buy a more expensive calculator, turns into a supercomputer, turns into a quantum computer. You know? And so it's very common that we do this kind of stuff. So it's just, you know, I want you to learn about successive approximations. You might go, I can ignore it because my calculator can always solve it, but I can, you know, I can put a problem in there that will make your calculator fail. I didn't do it in this last exam, but I could do it, you know, in a future exam. So just learn how to do the successive approximations method. But anyway, we come up with an answer here without, you know, even though there are a lot of steps here, you don't have to do this for full credit. And the pH comes out to 6.8956. So it's like water. And so the equilibrium concentrations here we can plug in. Oops, well, I guess.
So is it typical for that process that we just did to lead us to a third order?
No. Well, for two equilibria, two equilibria is the easiest, right? And then if you had 3 simultaneous equilibria or 4 simultaneous equilibria, then it's going to be more horrendous. But we're just sticking with the same. So this way, even though it might seem hard, this way might be easier than the approach in the book, you know. The approach in the book, I have it worked out too. I just forgot to scan it. Or I got to look it up. I'll do that. And so you can compare the two methods and see which one's easier. And then we double check. You see the hydronium is the same for both equilibria. And then the K's check out. So the K for step 1 checks, 6.2 is what it's supposed to be, times 10 to the minus 10. And the K for step 2 checks, it's 1 times 10 to the minus 14 is supposed to be. And so when we double check the K's, they work out, and the common ion has the same concentration in both equilibria. Versus if we did this stepwise, we would have seen a significant jump in the hydronium, and it wouldn't have worked. Okay. But you're going, this is not a math class, so you know you shouldn't have to do this. And that's correct, you don't have to do this. The other method might be easier. I don't know. But I have the other method worked out. The book doesn't completely work it out. It just gives you hints on how to work it out. But what we want to do is we want to avoid having to do simultaneous. Because if we have to do simultaneous, that's going to be a problem. So what we're going to do here is we're going to take a look at this and see if we have to do simultaneous or not. And so this is going to be 0.15, this is going to be 0 molar here. So we carry down the common ions here. Now, the change is going to be minus X molar, plus X molar, plus X molar. So at equilibrium, I'm going to have 0.15 minus X molar, 0.15 plus X molar, and X molar here. This K, I can already tell that this stepwise is going to work. The reason I can tell that this stepwise is going to work is I compare K for step 1, 10 to the minus 3, versus K for step 2, 10 to the minus 8. So step 2 is 5 orders of magnitude smaller. If it's 5 orders of magnitude, it's quite weak, and we don't expect it to be much of a contributor. And so if I was only interested in pH, I'd look at the Ks and go, I don't think I need to go to step 2, because I don't expect to form much additional hydronium in step 2. But let's see how much hydronium we form in step 2. And so this is going to equal the hydronium concentration times the monohydrogen phosphate divided by the dihydrogen phosphate. And so this is going to be 0.15 plus X times X divided by 0.15 minus X here. I'm not going to debate the simplifying assumption. I'm just going to go ahead and apply it. Hope it works. So a 0.15 plus X will just be 0.15, and 0.15 minus X will just be 0.15. And we're just assuming that X is negligible. And this is going to be times. And so you can see the 0.15s cancel. And so the math is really easy here. There's really no math. This X is equal to 6.23 times 10 to the minus 8. Now we do the percent change. Percent change, when we're looking at orders of magnitude, I just do this orders of magnitude. The change was 10 to the minus 8 on that order, and the initial was 10 to the minus 1 on that order, times 10 squared. And so this is about 10 to the minus 5%, roughly. About a 10 to the minus 5% change. 10 to the minus 5% change means I wouldn't even think about doing the quadratic for this one. That percent change is so small that the simplifying assumption is going to work really well, and I have high confidence in this answer. And so I'm just going to go with this answer here.
How does that work, since we used a molarity initially that we didn't have high confidence in?
Well, that we'll have to take a step back. I'm just saying in this quadratic versus simplifying assumption, I have high confidence. In my 0.15, I don't have high confidence. It should be close to 0.146. So rounding from 146 to 150 is introducing error there, or 150 versus 140. Although you say, it depends on the calculation. For some calculation, 146, 150, close enough. For others, you would be like if you're doing calculations for the launch to the International Space Station, you probably want to, be a little bit more precise. And that goes for, there's a famous story about the satellite. Did you hear that famous story? I think they already use high precision for everything, but the units were wrong on the satellite. It was like $40 million satellite that got destroyed. $40 million, wow, that's a lot. All right, so this is going to be minus 0 point, and then I'm going to put 7 zeros, 1, 2 after the decimal. 3, 4, 5, 6, 7, and then a 6, 2, 3. And so, yeah, you're right, 0.15 is not the most, but we're going to go ahead and do this just to see how much we lose. So I need 1, 2, 3, 4, 5 nines, and then a 5, 7, 2. Did we lose much? Dihydrogen phosphate?
How is it 572?
Oh, no, it's not 572. It's 272. 277. Okay, thank you. 377. 377. Yeah, 377.
Imagine we did all that work just to get that far.
I'm sorry?
Imagine we did all that just to get that far.
Yeah, well, we could check. When we double check our K value, then that's where I usually catch my mistakes. That's why I noticed a lot of people didn't double check their K values. I always double check my K values because I always make mistakes, a lot of them, so it's good.
How many zeros is that?
This?
Yeah.
This is 7 zeros. All right, this will be easier for me to add. 0.15, and then I'm going to add 5 zeros. 1, 2, 3, 4, 5, and then a 623. And then over here, this is just 6.23 times 10 to the minus 8 molar. All right, and now I'll check my K value. I'll just carry all these digits, even though it seems cumbersome. It is. You probably could round it and still be all right, but I'll carry all of them. 1.15, and then 5 zeros. 1, 2, 3, 4, 5, and then a 623 times 6.23 times 10 to the minus 8. Oops, I made a mistake. 1.15, 1, 2, 3, 4, 5, 0, 623 times 6.23. Did somebody already calculate it? 6.230005 times 10 to the negative 8. And so that looks good. Now, the problem is we have to look and see if that's going to screw up our previous K. So what we do is we take these numbers and then plug them back here. And see, did it change much? And so, one thing is, we can just eyeball it, or we can actually do the calculation. So in step 1 it was 0.15. In step 2 it's 0.1499999. Did it change much? No. Negligible. In step 1 it was 0.15. In step 2 it's 0.1500. Did it change much? No, it's negligible. So what we can say is that step 2 does not perturb step 1. If step 2 perturbs step 1, do you know what we do? We just kind of set it up and say that we have to do simultaneous, and that should get you full credit. Fortunately, if you want bonus credit, you can do it. So if you like, you want to try some mass and charge balance, you could do that and get some bonus credit. If I give you a problem like that, you can try it out. And so we don't have to worry about it. Did it change the pH much? The pH is the negative log of the hydronium. Are we going to get the same pH? Yeah. So if I were only interested in pH, I would have saw the K's. I would have saw the K went down by 5 orders of magnitude or 3 orders of magnitude or whatever it was, and thought, okay, it's not. However, that's for pH. pH you might be able to get away with step 1. Maybe step 1 and step 2 might be necessary in some cases. I'll tell you when in a little bit, but in this case, we're okay. Now, if I ask you for the inventory, then you have to do all the steps all the way to KW. And so we're going to do the inventory for this. And so I'm going to go to step 3, step 4, and maybe more steps. So step 3 is pulling off the third hydrogen off there. And so the last remaining hydrogen is on monohydrogen phosphate, and we have H2O liquid, and this is going to produce hydronium and phosphate here. All right, this is Ka for monohydrogen phosphate, which is equal to Ka3 to pull off the third hydrogen off phosphoric acid, H3PO4, which is equal to 2.2 times 10 to the minus 13 off our table there. 2.2 times 10 to the minus 13. You look at that, are you going to get much more hydronium from this step? No, practically nothing. And so the initial monohydrogen phosphate, that's common ion. And so what we're going to do is we're going to drop that down. It's 6.23 times 10 to the minus 8. So this is going to go down to step 3. And the other common ion is hydronium. That's going to go down to step 3. However, dihydrogen phosphate, this is the end of the line for dihydrogen phosphate. That does not go down here. And so over here, this is 6.23 times 10 to the minus 8. Water is pure liquid. And the hydronium is going to be 0.15 and then 5 zeros, 623. And then the phosphate's going to be 0 molar. And so the change here is going to be minus x plus x plus x. And so at equilibrium, I expect to have 6.23 times 10 to the minus 8 minus x molar, 0.150000623 plus x molar, and x molar. So we'll put this into the equilibrium constant expression. The equilibrium constant expression is going to be the hydronium times the phosphate divided by the monohydrogen phosphate. And so this is going to be 0.15 ... plus x times x divided by 6.23 times 10 to the minus 8 minus x. Now this is the tail of two x's here. What I mean by the tail of two x's is that the changes are different. So losing or gaining x here with initial of 0.15 is, we could say, is relatively small. However, here we're going to lose x, but our initial is extremely small. Do you see that? And so I'm really worried about the denominator here because I want to use a simplifying assumption, but it looks like for the denominator it might be pushing it. And so what we might have to do is we might have to do advanced simplifying assumption. Do you know what advanced simplifying assumption is? Advanced simplifying assumption is we just do it from the numerator. 0.15 plus x is just 0.15, and leave the denominator as a binomial. That makes it a little bit easier, but I don't want to debate this. I'm just going to do it for both, you know. And if it fails for both, then I'll think about doing advanced simplifying assumption. And so what I'm going to do is I'm just going to go ahead and try it. And so what I'm going to say is that x is going to be much smaller than 6 times 10 to the minus 8. I don't know if that's going to work, but we'll try it. And so this is going to be 0.15 ... times x divided by 6.23 times 10 to the minus 8. And therefore x, let's go ahead and calculate what x is. So x is going to be 6.23 times 10 to the minus 8 times 2.2 times 10 to the minus 13 divided by 0.15 zeros, 1, 2, 3, 4, 5, 6, 2, 3. I'm going to use the whole number because I have, my phone I think carries a lot more digits. So I get an x of 9.1373 times 10 to the minus 20. Now that is really small. So, you know, I think the percent change might be okay. So let's calculate the percent change. The percent change is going to be x, well, we'll just do it order of magnitude. Order of magnitude percent change is going to be 10 to the minus 20 divided by my initial, which is 10 to the minus 8, times 10 squared percent. And so that gives us 10 to the minus 12, 10 to the minus 10%. This actually worked out way better than I was thinking. 10 to the minus 10% is really good, isn't that? It's really good. So I'm not even going to think quadratic, and I'm not even going to think advanced simplifying assumption. I don't need any of that because this has turned out to work pretty well. And so what I'm going to have here at the end of this is this. I'm going to have 6.23 times 10 to the minus 8, and then I'm going to convert this to 10 to the minus 8. So that means I have to get rid of 12. So if I make the coefficient bigger, I got to make this smaller by 12. So I'm going to add 11 digits, 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then I'll go 9, 1, 3. I'll just carry those three. So this is times 10 to the minus 8. And so this is going to be 6.23, 0, actually, how many zeros? 0, 0, 9 zeros, I think.
Yeah.
Thanks. 973 times 10 to the minus 8. Did step 3 perturb step 2 by much? No. This is barely anything.
So are we subtracting or adding?
Oh, subtracting, sorry. Should be 2, 9. Actually, I was adding. 229. 22999999999, etc. Did it change it? Barely. We barely lost anything. And this one I need to add. So this is going to be 0.15, and then 5 zeros, 1, 2, 3, 4, 5, 6, 2, 3. So that takes me 3, 6, 9, 10, 11. 11, and I need to go 19. So I need 8 zeros on top of this. 1, 2, 3, 4, 5, 6, 7, 8, and then a 9, 1, 3, 7. Did this add much to this? No, so it doesn't perturb. So far we're safe. And then finally this is going to be 9.137 times 10 to the minus 20 molar. I'm just carrying extra digits, and I'm not consistent here with the number of extra digits here because it's always a choice between speed and accuracy. All right, but to get the full inventory, there's one more hydronium contributor in this acid solution, and that's going to be Kw. And so I need to do step 4. Step 4 is going to be H2O liquid plus H2O liquid. And this is going to give me hydronium and hydroxide. And the hydronium I'm just going to carry from step 3 down to step 4. And so this is going to be 0.15 ... a molar. And this is going to be 0 molar here. That's my initial. The water is a pure liquid. So this is going to be plus X from water. And so I'm going to get 0.15 ... plus X times molar and X molar here. So solving for Kw, Kw is just the hydronium times the hydroxide concentration, which is going to equal 0.15 ... plus X times X. Now, this is equal to 1.0 times 10 to the minus 14. And because of the common ion effect, I have a lot of hydronium in here to begin with, 0.15 ... That's a lot of hydronium. So X is going to be very small, like 10 to the minus 8, 10 to the minus 9, 10 to the minus 10. So X is not going to be significant compared to the hydronium, but X will be significant compared to 0. You know, anything's significant compared to 0 because what is 0? Nothing. So if you have something, it's better than nothing. And so we'll do this, the simplifying assumption here. And so this is just going to give us 0.15 dot 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 times x. And therefore x is equal to, and I'm going to punch in the whole number here. Maybe I'll punch in the whole number if I can remember it. So it's going to be 1 times 10 to the negative 14 divided by 0.15, and then there was 5 zeros, and then a 623, and then another 9 zeros. I don't think your calculator can do this, but let's see if mine. 3, 6, 7, 8, 9, and that was 137 equals. Okay, and then I get this. I get an x of 6.6663 times 10 to the negative 14. So it's so it doesn't really perturb. I mean, 10 to the negative 14 versus 10 to the negative 2. Are we out of time? Shoot, I was thinking we went to 11, but I mean 1. But here, I'm going to stop here. We'll finish this